the University of California, Merced. He received his bachelor's and master's in science in electrical engineering with a communication systems specialization from Shiraz University in Iran in 2013 and 2016, respectively. His research interests include machine learning optimization algorithms, statistical signal and image processing, neural networks, and statistical pattern recognition. Pooya's research spans a diverse set of problems, including optimization of partition-wise machine learning models, such as decision trees and prototype nearest neighbors, and the applications of novel machine learning techniques in epidemiology, unsupervised learning, and training under adversarial attacks, which I believe is related to today's talk. Pooya has published more than 10 papers in top venues during his PhD, including NeurIPS, AAAI, and ICIP. Pooya, thank you very much for joining us. The floor is yours.
So first of all, thank you everybody for joining this presentation. Today I'm going to present the work Adversarial Poisoning Attacks and Defense for General Multi-Class Models based on Synthetic Reduced Nearest Neighbor. So I did this work with my collaborators, Dr. Behzadan, Dr. Tavallali, and Dr. Singhal. Dr. Behzadan from the University of New Haven, College of Engineering, Tagliatella, and also Dr. Tavallali from NASA JPL, and Dr. Singhal, who's my also advisor at UC Merced Electrical Engineering Computer Science Department. So the outline of this presentation is as follows. First, I'm gonna present the adversarial poisoning attack based on synthetic reduced nearest neighbor. So essentially this attack is going to be based on the modalities of the train set and data set. So it has 4 parts. I will first explain the problem. I will also first give some literature review and motivation of the problem. And then I will present the optimization algorithm regarding this attack, which is going to be essentially the attack itself, the attack algorithm. Further, we will give the analysis of the attack technique. We will give some boundaries and what is the computational complexity of the attack. And then finally, I will present experimental results and compare the method to the other similar attacks that can be defined under the description of this attack. So then what I'm gonna do is to present a robust, or as the defense technique, we are going to present the robust SRNN, which is the defense against this attack, and the optimization algorithm is actually based on EM algorithm. I will present the problem, the optimization steps of the RSRNN, and analysis of the RSRNN. Then finally, I will present the experimental results of the RSRNN. So as the start and the related work, or kind of the motivation for this paper, I need to mention that most of the machine learning models are known to be vulnerable to data poisoning. The data poisoning, in the data poisoning, the adversary can either perturb, add, or remove samples from the data set. And what is the goal of the adversary? Simply, the adversary's goal is to deteriorate the integrity of the model or to make the model perform poor in practice. So when I talk about the model here, I mean the user model. So adversary makes some changes to the train set that the user can use. And after that, the user will train its model over this train set. And these changes will potentially cause the user to lose accuracy and performance during the testing. So generally, to make these problems more realistic, the attacks are constrained to an attack budget. For example, the number of samples that the attacker can perturb or make some kind of change, or for example, the amount of perturbation, for example, the distance between the features and the perturbed features of the samples. The changes to the training samples potentially can be seen as modifying the modalities of the data. And the main goal, or the main target of every adversary, is to deteriorate the consistency of the train set and the trained model. So Much of the poisoning attacks are focused on targeting a specific models such as SVMs or neural nets and other specific models. These attacks usually focus on targeting the training algorithms, which means that it is assumed that the attacker knows the training procedure of the algorithm, which it might be true or not true. It'd be depending on the cases. So the label flipping attack. So the main focus of this paper is going to be on label flipping attack. So the attack that we are presenting is going to be a label flipping attack. But what is label flipping? Simply, it consists of perturbing or changing the samples labels. Again, it is constrained to similar to other attacks to a budget, and this budget is explicitly the number of samples that the attacker can change the label. The attacker tends to maximize error of the user's model over the test set. And I must mention that's optimal attack of such algorithms is NP-hard. So finding the optimal attack is NP-hard. So the algorithms used for label flipping are either based on differentiable loss functions. This means that if the loss function is different, for example, if the model is a decision tree or a forest or let's say RBFSVM or AdaBoost, these algorithms cannot be applied to them. They're limited to binary classifications mostly, and limited to specific models or training procedures. So essentially, this is saying, okay, what's the limitations of the existing attack? So the motivation of our work is to propose a general label flipping attack based on modality of the data. So we want to propose an attack that can affect any model and under any kind of classification problem. And it is also not restricted to only differentiable loss functions. So similar to the attacks, most of the defense or attack techniques are, again, limited to specific models, binary classification, differentiable loss functions, and defense techniques specifically are restricted to type of attacks. The attack can be seen as noise also in the label. So if you look at the attack from a noise point of view and we say, okay, the label flipping attack can be seen as noise in labels, then we have a vast literature on the label noise, and some of them are actually similar to the attacks defined in the literature of the adversarial data poisoning. So in general, these techniques are divided up to three general types. The first type is noise completely at random. This means that any sample's label can get perturbed randomly, and it is completely, the probability of labels getting changed is equal for every sample in the train set. The noise not at random is the second type. The good example of it is that the noise can happen at the decision boundaries of the modes of the data or the decision boundaries of the classes or whatsoever. So this means that maybe something has caused the labels at the boundaries to get changed, and the decision boundaries, which are very crucial, will get changed in some shape or form. So the third one is noise at random. However, this specific type of noise consists of a specific class. So for example, what happens here is that one of the classes is having random labels, or the labels are somehow perturbed to another specific class, or they are randomly distributed among other classes. However, usually this type of attack is easily perceivable or recognizable by a human oracle or somebody who's checking the labels and sanity of the labels of the classes. It has also been shown that the various models are resilient to noise. So here, finally, what we are going to do is to propose a modality-based model-free attack, and we will propose a defense technique based on the modality that can also defend against this attack. So, but all the time I'm saying that adversarial poisoning attack based on SRNN. So what is SRNN? What is synthetic reduced nearest neighbor? So first of all, nearest neighbors and synthetic reduced nearest neighbors are among the oldest models. They are popular because of their simplicity, competitiveness, and they can intrinsically handle multi-class classification tasks. Okay, so in contrast to, for example, SVMs, logistic regression, some of the boosting algorithms that can only handle binary classification problems. So The SRNN model, what is it itself? So the SRNN model itself is similar to a k-means, except that your train set is supervised. Okay, so what does it mean? You can think of it also as a nearest neighbor. So here we have k-centroids in the feature space of the sample. So centroids act the same as a nearest neighbor model. So what does it mean? This means that when we have an input, that input gets compared with every k-centroid, and the closest centroid will do the prediction for the input. So each centroid is also associated with a label. Okay, so that's why it is a kind of nearest neighbor model. It is also known as prototype nearest neighbor because these k-centroids can be thought of as prototypes, and a prototype is essentially similar to the train set. It looks like the samples of the train set, and in some shape or form, it is representing the data set itself. So also it is known that each centroid represents a mode of the data. You can think of it as the data is being produced by several distributions, and each of these distributions can be recognized by one of these k-centroids. So the training of the SRNN consists of finding k-centroids that minimizes the misclassification error over the train set. And the k is user-defined hyperparameter, which means, okay, the user can define, I want like 10 centroids, 20 centroids, or whatsoever. And also, as you will know, in the machine learning, we train our model over the train set in the hope that it would do good at the test time and perform good at the inference time. So one important thing, which is, so the question here is that how did the SRNNs came to exist, which I'm gonna a little bit explain it here. The nearest neighbors has high inference complexity simply because when you use your whole train set as the nearest neighbor, any input should get compared with every single sample in this train set. So that's a huge amount of inference. So researchers in the literature decided to investigate and solve this problem either by introducing some data structures such as decision trees or cover balls. And neither of these models are interpretable or storage efficient. They also suffer from curse of dimensionality. In some researches, people have tried to reduce the dimensionality of the model, the train set itself. And the third method consists of reducing the train set by removing redundant data or learning prototypes by softening the nearest neighbor rule at inference. So essentially the second method, the second part of the third approach is where the prototype nearest neighbors or synthetic reduced neighbors have been introduced. Simply by learning some new samples that can be used as the nearest neighbor model. So the SRNN problem is as follows. Let's say we have n pairs of observations, x of y and y of y. The x is the features in the real space with dimensionality of d, and the y is the labels of these samples or the classes. These centroids or prototypes that belong to the SRNN model consist of a set of centroids or prototypes each centroid has a place has a position in the space of the features, and it also has a label. So there is also k number of centroids. So the inference, as I said, is the prediction of an input is the label of the closest centroid to that input. So here is the minimization problem that we have here. Simply similar to every machine learning problem, we need to define the problem to minimize the mismatch between the labels of the true labels of the samples and the prediction of the model. So NN stands for nearest neighbor function, and here the constraints define that. So here we use the 0-1 loss classification, and the constraints over NN consists of giving the label of the closest centroid, and we also need to perform an action and find the closest centroid. D is a distance function, and it represents the distance between let's say, x of I, which is the input, and all of the centroids, which returns the index of the closest centroid. So throughout this presentation, the J star of I represents the index of closest centroid to the ith sample. So now let's go to the modality-based adversarial label flipping. So up to this point, we now know the SRNN. We know that the SRNN centroids represents the modes of the data, and now we are interested in introducing an attack which is based on the modality of the data. So this objective function in this problem might look a little bit complicated, but I'm gonna make it simplified. As I said, the adversary is interested to change the data set such that the performance of the trained model by the user is maximized. So that's why, first of all, we see a maximization. And here we see the loss function, which would like to, in here, which we would like to increase the mismatch between the labels of the X of I and the prediction of the model, the trained model by the user over X of I. So what is the NNN star? NNN star is the optimum model trained over the train set. So keep in mind that the previous minimization that we saw has been moved to the constraints of this new problem. So essentially, this is like we want to maximize the loss, while at the same time, we know that the user is going to minimize something over the train set. So actively, and as you can see, the constraints of the previous, the problem of the SRNN are moved inside the constraints of this problem, which is these three constraints here. So the new constraints here that we have is the S of P, which is the poisoned data set. And that is what the adversary is going to do. And that is what's going to be the train set seen by the user. Here, the Y of IP represents the perturbed label, and Y of I represents the true labels. And we have an indicator variable or indicator function that is either 0 or 1. And if it is 0, then this means that the adversary did not select the ith sample. And if it is 1, this means that the adversary has selected the ith sample. So as you can see, this is a kind of selection problem. Okay, so the question for the adversary is to select which samples and how to perturb the labels of these samples. So this problem is NP hard, and it is known in the literature that it is NP hard. So finding the global optimum of this problem is not practical, simply because the different combinations of the samples and then training at the same time the user model over the selection is by itself very hard, and it takes a lot. There is so many combinations. So what we do here is to propose a greedy algorithm that can train over, that can satisfy these constraints while at the same time approximating the solution. So the greedy algorithm consists of first training the NN star over the train set without changing any of the labels. At the same time, we are also going to fix the centroids. So if you look at this problem and the previous problem, what you can see is that the constraints over the NN star has been removed and replaced with some simpler constraint, which I'm going to explain in a moment. So also keep in mind that the previous constraints regarding the selection of samples is still here. And we have also another, this was also previously in the previous function, previous problem already there. So this is the cost, this is the maximum budget of the attacker. So here the budget of the attacker is the maximum number of labels that it can flip. So the only constraint that has changed now after training the NN star and fixing the centroids is the labels of the centroids. This is the labels of the centroids that the user model will learn. So how can the label of a centroid be learned? Okay, so if we fix the centroids, the set of samples that get assigned to the jth centroid is fixed, and we call it the S of JP. And since all of them get predicted by the label of that centroid, this means that the label of the centroid is similar to optimizing a constant predictor function. So in a constant predictor function, we always predict as the majority of the labels or samples assigned to the jth centroid. So that is how the Y of J hat can also get changed. So it means that if we want to change or perturb the label of the jth centroid, we need to at least make sure that the majority of the labels in the Sj of p, or the set of samples assigned to the jth centroid, are perturbed and changed. So an intuitive approach is to just randomly change half plus one of the labels in Sj of p to the minority class in that set. Okay, maybe the minority class is a class with no samples in that cluster. Why? Simply because in practice that can happen if we have a good data set. Ideally, the clusters are different and they can be pure. Okay, so this is just an idea. Okay, let's change half plus one of the labels in Sj of p to the minority class. So this means that the cost to change or perturb the label of the jth centroid is equal to number of samples in that samples in that assignment, in that set that are assigned to the jth centroid, divided by 2. So now the problem is we now know what's the cost of changing the label of each cluster or each mode of the data. Now the problem consists of selecting the centroids or selecting the clusters to attack, because at the end of the day we have some limit over the budget of the attack. So then this simplifies the problem. We can rewrite the problem as to maximize the cost of j times I of j, while we make sure that the summation of the costs that we have spent over the perturbing labels is less than the budget, because we don't want to violate the budget. Because this way we also make sure that these clusters, the centroids of these clusters labels will get changed in that way. So to solve this problem, either we can apply a greedy algorithm or we can apply dynamic programming, and they can easily solve this problem. So for every flipped label, it is shown in the paper, and you can read the paper, it is on the archive. For every flipped label, 2 errors will occur. So this means that if the budget is something, we can increase the error by 2 times that cost. Okay, that's an upper bound. So the initial model takes O and dk. N is the number of samples, D is the number of features, and K is the number of centroids. And applying the label flipping step itself will take O n, which is very fast. So in the experiments, what we are going to do is to compare the SRNN attack with several other label flipping attacks. Essentially, we have taken those label flipping attacks from the literature of the label noise, and these other attacks are designed in a way that they can affect any machine learning model. Okay, so we also, at the same time, to see the performance of the attack, what we do is to train several resilient models to these attacks. So at the same time we perform these attacks on the data set, it is like creating several new data sets and then training all of these models over these data sets. So this is what's going to happen. Here we have the set of attacks. No attack, the SRNN attack, the NCAR, which was noise completely at random, noise not at random. In the noise not at random, what we did was to train a huge forest and the forest of decision trees. And in that forest, we defined the decision boundary based on the confidence of prediction by the forest. So, and then what we did was to change the label of the samples on the decision boundaries to the second highest probability class. Here, the models that we are presenting are the SRNN model itself, the decision trees, which is known classification and regression trees, the oblique classification trees. The oblique classification trees are essentially more powerful than the regular decision trees, simply because they use linear classifiers at the nodes of the classification tree. And then we also compared with the RBF SVM. In the RBF SVM, the thing that we did was to first learn a k-means model, and then we fit RBFs on this k-means model, and then we learned a SVM on top of it. So this means that these RBFs are essentially working like a feature extraction for the SVM. So and the hyperparameters of the RBFs were defined using a validation set. So we're set using a validation set. So what happens here is that, as you can see, the colors represent the data set, okay? And the model trained over this perturbed data set are represented by the lines. The horizontal axis shows the number of basis functions. For example, for a tree, the number of basis functions can be the number of leaf nodes. For an RBF SVM, it can be the number of centroids, and essentially for the SRNN, it is the number of centroids. So for the same curve, what we would like to see is that SRNN should do more, should achieve more error, higher error compared to the others, simply because we are the attacker and we would like to make the model to underperform. So by looking at it and comparing various curves, we will notice that the SRNN was competitive and could increase almost the error of all the models. Okay, sometimes it is occasionally, maybe in some cases, that the SRNN could not increase the error as much as like the NNAR or NNNAR ADA boost. So, but in general, it can increase the error of all the models. Here we also have experimented the test error for 5% attack, which means 5% of the labels are perturbed or 10% of the labels are perturbed. So to make it more competitive, what we did was to look at each data set, each perturbed data set, and pick the smallest test error defined by all the models, found by the performance of all the models. So this causes the comparison to become competitive, because sometimes a model under some noise would perform better than another model. So this can be varying in various ways. So this means that if we trained several models, here we are reporting the best test accuracy of them for a specific attacks. And as you can see, the SRNN could increase the attack on these data sets very drastically, and for all the models actually. For more experiments and more details, such as these experiments, you can look at the paper and the supplemental materials of the paper. So now, after introducing the RSRNN, now I'm going to talk about after introducing the SRNN attack, I'm going to talk about the RSRNN, or robust synthetic reduced nearest neighbor, or the regularized synthetic reduced nearest neighbor. This is the defense technique that we are introducing. So this defense technique actually can detect and exclude the flipped samples on the fly. So the samples that are under attack, that their labels have been changed, can be recognized and not used during the training procedure on the fly. So what are the regularizing terms that we have added here? So we have added a new regularizing term, which is the confidence range of each centroid. So essentially, this means that each centroid will consider a sample as not malicious if it is inside the range of this centroid. So for each centroid, we have defined a range, and these ranges are different for each centroid. I mean, it doesn't mean that all the centroids will follow the same range. So for each centroid, that's different. So samples, at any sample that is beyond this distance, beyond the range, the confidence range of the centroid, is considered as malicious. And here, the distance between the ith centroid and the ith sample and its closest centroid is defined as R of ij star. So this is for simplicity, so that we don't need to use this longer term for the distance between the centroid and the sample. The cost complexity function is over each centroid is the second regularization term that we have added here. This helps and facilitates the procedure of training to prune some of the centroids and clusters. This also helps recognize the attacked modalities of the data. So essentially, this cost complexity function, if you're familiar with the context of decision trees, this is similar to the cost complexity function defined over the structure of decision trees. So now the objective function for the defense technique. So as you can see, again, the objective function consists of parts of the original SRNN. However, we also have added the regularization term for each centroid. The lambda is coefficient of these regularizations, these ranges for each centroid, and alpha is the coefficient of the cost complexity function. So the NN, which was our model originally, would determine the label of the samples depending on their distance and the confidence range. Also keep in mind that always NN returns the label of the closest centroid. If the sample is inside the confidence range of that sample. Otherwise, they are considered as malicious. Just as a reminder, the J star of I represents the index of the closest centroid to the ith sample. So to optimize and solve this problem, we follow the EM algorithm that was previously also used to optimize such problems. This time, this optimization consists of 3 steps: the assignment step, the update or centroid step, and the pruning step, based on a validation set. So if you are familiar with the K-means algorithm, the K-means algorithm has 2 steps, the assignment step and the update step. In the assignment step, and these steps are kind of similar to this EM algorithm. So the first step, which is the assignment step, has 2 parts. So the first part consists of finding the samples that are assigned to the jth centroid. So essentially, this means that for a set of samples, the jth centroid was the closest, and that consists of the S of J, and that's a part of the assignment step. The second part of the assignment step consists of finding the optimal labels for the jth centroid. So this means that we can represent it by a loss function here, and the U is the step function. Keep in mind that, as I said, the best label for this centroid is going to be the majority of labels assigned to this centroid. However, here, you also have a confidence range. So the best label now consists of the samples that are inside the confidence range and the majority of those samples, the majority label of those samples. So this is the problem for the assignment step, actually. So now we have the updated step. Updated step consists of updating the centroid's position and range. So keep in mind that the centroid labels are kept constant. So when we want to optimize a centroid, we assume that the rest of the centroids are fixed. And now we apply an alternating optimization. Okay, so one step is to first optimize only over the position of the centroid. So this means that we keep the ranges fixed also, and we only optimize over the centroid. So this optimization can be written as follows. So for when we want to optimize the centroid, 2 things can happen. Okay, so one is that when we move the centroid, the assignment of samples can get changed. Some of the samples will get changed to the jth centroid, and if the jth centroid goes too far, those samples can get assigned to the rest of the centroids. Okay, because simply the distance between the centroid and this sample is larger than the distance of this sample and one of the closest centroid from the rest of the centroid. So essentially, this is a problem that we need to determine. The sample should go either assigned to the jth centroid, or it's better for the sample to get assigned to one of the centroids from the rest of the centroids. So here, this is an NP-hard problem. The first term shows the sample getting assigned to the jth centroid. It is also accounting for the confidence range, which is the R of J. If the sample is outside the confidence range of the jth centroid, while jth centroid is closest to it, again, we are going to still have another loss. Okay. So, and the second term consists of the samples that are assigned to the rest of the centroids. So with this, we now see that there is a problem here, and that is how to assign the samples. Either we should assign them to the jth centroid or to the rest of the centroid. So as you can see, this is a kind of binary classification problem, except that we really don't know where we should assign the sample. That's also the relation between the EM algorithm and this algorithm, which is finding out which set that we should assign the sample to itself is equivalent to calculating the posterior probabilities in the EM algorithm. So the details of the relation are given in the also paper, and I'm not going to discuss that here, but it's interesting anyway. So based on these different assignment of the samples to either jth centroid or one of the rest of the centroids, 8 situations can happen. Either the sample can get classified wrongly if it's assigned to the jth centroid, and it can get classified wrongly if it gets assigned to the rest of the structure, and also the rest of the structure might decide that this is a malicious sample. So in this case, we cannot do anything. The changing position of the jth centroid is not going to make any change to the fate of prediction for that specific sample. This is also true even if the rest of the structure would not define that sample as a malicious sample, simply because the rest of the centroids could not correctly predict the label. So but there are some situations that something can happen. Okay, so again, if the sample assigned to the current centroid, to the jth centroid, get classified wrongly, but get classified correctly by the rest of the centroids, however, considered as malicious, nothing can be done about it. This part is actually interesting because this is somehow discarding the malicious samples. So some of the samples can get classified correctly only if they are assigned to the jth centroid, but not correctly if they are assigned to the rest of the structure. So we would like this, if they're going to get classified correctly if they are assigned to the rest of the centroids and not malicious at the same time. So these are the samples that should get assigned to the rest of the centroids. For these other scenarios, the sample should get assigned to the jth centroid either because it was being classified, as malicious or being recognized as malicious by the rest of the centroids, or it would just simply get classified wrongly by the rest of the centroids, or both. So these 3 type of samples should get assigned to the jth centroid. And if a sample is always getting classified correctly and not being recognized as malicious, so again, that's not an important case anymore. So based on that, we can write the problem based on these optimum assignments. Okay, so we would like to assign the samples to these centroids. So then we can again redefine the original problem that we had here to this other problem. We are interested to assign the Sj star to the jth and Cj star to the rest of the centroids. C stands for complement of the jth centroid. So this means it only consists of the rest of the centroids. So, however, this problem is still an NP-hard problem. This is a binary classification problem. You can think of it as like a problem for example, SVM. In the SVM, we were interested to separate 2 groups by a linear classifier. But here we don't have a linear classifier. There's a centroid that we can move, and there are several other centroids in the space. So similarly, similar to the SVM, we are going to introduce a surrogate objective function that by minimizing this surrogate objective function, we are making sure that we can decrease the error of such, we can find a good minimum of such problem. Okay, and this actually objective function has some relations to the hinge loss of the SVM. So, but anyway, I'm not going to go into details of that because of the lack of the time. But if somebody has a question, I can answer it later. So, up to this point, we optimize the position of the centroids. So we do this optimization for each centroid, and then we go over the R of J. R of J is the range of the confidence range of the centroid. When we fix everything and we want to find out the confidence range, the samples that are assigned to the jth centroid are laying in some distance from the jth centroid. So essentially, we can sort these samples based on their distances to the jth centroid, and using an incremental algorithm and the label of these samples compared to the label of this jth centroid through some incremental algorithm, we can find the best confidence range for that centroid. So this is also the update step. After iterating over the update step and the assignment step, we have the pruning step. So it is similar to the pruning of the decision trees. We are going to prune any centroid whose removal would increase the validation set. The cost complexity function that we used was the Gini index. And also keep in mind that the data sets in the integrity can be under question, which means that some of the samples labels are flipped by some adversary. So here we also not only remove the centroids, we also remove the samples, and we also check the training, we check the new model with the validation set. We need a clean validation set. However, this even a relatively small portion of the train set would be enough. Here, what we did was in our experiments, we noticed that something like 8% of the whole train set used as the validation set, used as the clean validation set would be sufficient. By clean, I mean the labels are not touched and the labels are true labels in the validation set. So what we did here was to, again, train RSRNN under the SRNN attack and compared with several other known models that are resilient to such attacks, to the general purpose label noise and the noises that I explained to you. So here we have the RSRNN, we have the RBF SVM. For the RBF SVM, again, we use the clean validation set. We have the tree in which the split function is the Gini index or the entropy. So it is known that by changing the split criterion, the resilience of the tree can get changed to the model, to the attack techniques or the noise techniques. So then we compared with the original k-means. What we did, we only ran the assignment step of our algorithm over it, and we assigned actually the labels using the validations. We also applied the AdaBoost to see how that would perform, and it is also known that the AdaBoost is resilient to several types of noises. So finally, I have explained these models also, so you can go ahead and read more about them in the paper. We also explored various attack budgets, 5% and 10%. So finally, the conclusion. The conclusion is that we have presented a novel model-free label flipping poisoning attack. So this means that this is the first poisoning label flipping poisoning technique that is not limited to only binary classification, a specific model, or gradient-based approaches. The attack technique is very fast, and the attack technique does not require the knowledge of the model. So as you observed as we observed with the experiments, it can deteriorate the performance of any model over the data sets. So we also proposed a novel defense technique based on the SRNN that can intrinsically detect and exclude adversarial samples on the fly. In the experiments, we noticed it could find to 80% of the malicious samples and remove them with a precision of 50%. So RSRNN has shown ability to achieve significantly lower test error compared to other known resilient models, and also it is scalable, and its training time and complexity is linear over the trains. So thank you so much for attending this presentation. Here are the papers that I have cited in this work. There are more references. You can look at them in the paper, and I would appreciate to know your questions now.
Pooya, thank you so very much for this excellent presentation, and I personally quite enjoyed it. Thank you for the perfect timing as well.
Thank you so much.
As many of my fellow researchers and students are aware, I always have a large number of questions, even about the work that I've been involved with, but I would like to first open the floor to any questions that the audience might have. I'm going to fill the silence with one of my own questions. So, of course, this is from a theoretical point of view, a very interesting piece of work. In practice, who would care about this? And let me ask my second question here as well. What are the assumptions made about the threat itself? What does the adversary need to know, and what is the adversary capable of doing in these sorts of attacks and corresponding defense?
Okay, good questions actually. So I'm gonna first answer the first question. So the first question was, who cares about these kind of attacks? So the thing is that in the literature, we have seen usually most of the attacks are either used for some specific model or used for some specific loss function, and they are, specific cases. Okay, and for example, one of the assumptions on these attacks is that the attacker knows, for example, the training procedure, the model, or something like that. So here, we wanted to introduce an attack which doesn't know these informations. And the attack is essentially actually based on the structure of the data itself, the distribution of the data itself. So rather than thinking about what would be the user's model, it is thinking, how can I deteriorate actually somehow interfere with the data structure, with the data distribution. So that I think should be the answer to the first question, because this is a real attack. Okay, so with this idea, if the attacker has access to the train set, that's the only assumption that we make. It can deteriorate performance of any user model. So regardless of what model you are going to use, this attacker has the ability to degrade the performance of your model and the integrity of any model that you have. So essentially, this attack is very important. So the second question was that what are the assumptions that our attack is based on? So I would say probably the only assumption is that we are assuming the attacker knows the train set, and it assumes that the models that you train are based on the modalities of the data. It's like it's assuming that the data set has been generated using several distributions inside the feature space of the data set. So what it likes to do is to kind of make these modes of the data incomprehensible to the user. For example, let's say the example of the spam and the inbox. In your emails, you would like to receive the important emails, and you would like to not receive the commercial emails regarding, I don't know, some specific pill or some, I don't know, some specific product. So the attacker here would do something that you are going to miss your important emails, for example, important emails from one mode of data, which is, for example, Professor Behzadan wants to send me an email. The attacker would do something that I'm not gonna see the Dr. Behzadan's email because of some specific properties there. So, or in the other hand, I'm gonna happen to see that, for example, the products of some companies appearing on my inbox. So even though this example that I gave was a binary classification example, still this attack technique can be applied even to multi-class classification problems and not only limited to the binary classification problems. So I think these are probably the most important parts to say, but Dr. Behzadan has a higher rank and knows better than me if he wants to add anything here also.
Not at all. I actually think that you answered the questions perfectly. I'm going to follow up on that after Pravin.
Okay.
Pravin?
Oh, hi, Professor. So my question is that you said it doesn't require any model information to attack a particular model or to deteriorate a particular data set or classification. So does that mean it doesn't require the future information, like how many features he trained the model, that kind of stuff?
So, Dr. Behzadan, can I answer?
Sure, yeah.
Okay, so that was a good question, actually. So this question that you asked is essentially means like, let's assume that we have a stream of data and maybe some future samples are coming in, or maybe some future models we are interested to train over the data set. So the answer is that we haven't yet extended to that, but that would be a cool question on how, as a future work, how can we extend to this setup and scenario. However, currently the proposed attack and defense are working in offline, okay, not in an online setup. However, I think it shouldn't be that much problematic to extend also to the online setup. However, that's a good question, actually. So that can be future work, actually.
Okay, thank you, Professor.
Thank you.
While we're waiting for the next question to come up from the audience, knowing the entire data set is kind of a rare occurrence in commercial settings. For example, in spam detection and spam classification, An attacker doesn't often have access to the entire dataset, labeled dataset of emails. Do you have any thoughts on how your proposed technique, both for defense and for attack, can be modified or extended to support cases where the attacker only has a subset of the training set or a small number of samples from the training set?
Well, actually, we did some experiments, but those experiments were like using 20% of the data set, 10%, 5% to see what's going to be the performance and how they are affecting the model. So as far as I remember, the model could provide some good, effective attacks. Even the train set was a smaller. Well, I think we can do also more experiments on that to more properly identify the fact that even if the whole train set is not used there and it is a poor portion of it is given, the attacker still can perform good, So, but as far as I remember on those experiments, the attack could actually increase the test error of all the models, even at like 20% or 10% or 5% of the train set was used. So it can do some good, but I think we can also explore that further. Yeah.
Very well, thank you. Binish?
Hey, Pooya.
Hi.
This is absolutely great. Wonderful presentation.
Thank you.
My question is about the hyperparameters like learning rate and all. Does it have an influence on how much you can kind of corrupt your model um, based on how you manipulate your or pollute your data set?
Okay, so how that can affect is depends on the NNS star. Okay, so I said that we first train a model on the unperturbed dataset, on the dataset with the true labels here. So NNS star itself, when we want to train it, since we use some EM algorithm, there is somewhere that we use some gradient descent stuff because of some surrogate objective function that we use. But I noticed that obviously the better if the NNS star is, the attacker is going to perform better. So this means that if somebody just throws some random NNS star, and it says it NNS star, okay, so some random thing is obviously not optimal. Some random thing would cause the attacker to don't perform that much, efficient, and that not that much to increase the test errors of various models. But in general, that matters in the aspect that the NNS star has to be as good as possible. Okay. Yeah. And also in terms of the number of the centroids that are used by the attacker, in all our experiments that I presented here, I showed only 30 centroids. For the attacker only uses 30 centroids, but we also explored to see what if the attacker uses another number of centroids, like 60 centroids or other stuff. And I noticed that, they can have some effect on this. For 60 centroids, I noticed that the attacker could do even more damage, but for simplicity here, I'm just presenting the 30 centroids. So these hyperparameters can affect the attacker, and the better model that you train, specifically the NNS star, the more efficient attacker it would be.
Thanks, Pooya.
Thank you.
I'm going to follow up on the question that Binish just asked. One of the things that is not mentioned in the paper as well as the presentation is the impact of the defense mechanism and the attack mechanism on deep learning models, or even models as simple as perceptron logistic regression and such. Do you have any thoughts on whether, first of all, this is a relevant question or not, and second of all, whether there would be any significant differences in terms of performance in comparison to the other benchmark models you've included in the comparison?
So you mean like the benchmarks in the computer vision and using the deep learning models?
How would a CNN model be affected if we were to apply this sort of attack on the data set.
Oh, I see. So the thing is that, the whole point of this presentation is that how this attack can affect the structure of the data, the distribution of the data. So this potentially can have effects on the CNNs, obviously, and the benchmarks of the computer vision, or I don't know, larger CNNs and stuff like that. So that thing, I would say, is probably a little bit not necessarily in the scope of this paper. Here we want to show that this attack can affect anything. So, but why CNNs are not considered here is because the CNN, it depends on the data set also. Okay, so we would like to introduce an attack that perform, that can be performed on any kind of data set, and it's a general setup. But the CNNs are good for only specific image classification problems. Okay, so I don't say that the CNNs are good or bad. I'm just saying that that by itself, we are like restricting our work maybe in some shape or form. So, however, our attack can also be applied into those setups. But probably we need to change a few things. We need to think about some feature extraction and, maybe going into another dimension, because we are using CNN, and CNN by itself is not like comparable to a forest model, unless under some certain, setups and assumptions.
Very well, thank you. Do we have any other questions from the audience? Okay. Pooya, thank you so very much for this excellent presentation.
Thank you so much.
I hope that our audience have benefited from this presentation. You are essentially the seminal presenter of this semester's series.
Thank you.
We seem to be off to a good start. Thanks again, Pooya. It was a pleasure.
Thank you, everybody, for participating.
And we look forward to your future work and extensions of this research in the coming months or years. Have a great weekend, everybody. I just want to quickly make an announcement that the seminar series will be regular. Hopefully we'll have a seminar at least once a week. The announcements will be made either on the Friday before each presentation or on the Monday preceding the presentations. The presentations will be scheduled mostly on Fridays around the same time. And if you're interested in learning more about the schedule, about the type of research that we do at SAIL, at our lab, feel free to check out our website or get directly in touch with us. Have a great weekend, everybody, and goodbye.
Thank you so much. Goodbye.